few minutes to let all of our attendees connect so that they can get all the amazing information that we're going to be sharing. In the meantime, if you would like to drop in our chat where you're tuning in from, maybe how many there are of you watching, is it you and your family? Is it a classroom? Is it you and your dog or cat? We would love to hear a little bit more about our folks tuning in today. Oh, we have an 8th grade earth science class from Wisconsin. That sounds awesome. Hello, this is great for earth science. Field trips, in-house field trips from St. Joseph's Academy. I don't know where St. Joseph's is, but welcome everybody. Like I said, for those of you who are just connecting, just trying to get a little bit more information about all of our attendees today before we get started. So please feel free to drop in into the chat where you're tuning in from, how many of you there are. St. Louis, Missouri, that's where I am actually located as well. So I love to see it. And Richard is from Columbia, Missouri originally. So some Missouri folks. We got New York, Tennessee. I absolutely love it. It's so nice that all of you are here to join us about our amazing, as we talk about this amazing program and this amazing facility that we have. So please keep throwing all that information into the chat. We will turn that chat off in another minute or two, just so that we can get focused on our ice core topic. But as we get started, I just want to introduce myself. My name is Sarah Eckert. I am a communication specialist at the U.S. National Science Foundation Office of Polar Programs. So my job is to help bring the amazing science that we support at the NSF to all of you. And a few reminders before we get started. All of our attendees are muted and cannot turn on their video. That's just to save bandwidth and also make sure that we can give this presentation as uninterrupted as possible. When it comes to Q&A, please use the Q&A box that is provided through Zoom. That is something that will be up the entire presentation. So as our presenter is talking, please feel free to throw in any questions that you have there. And we might not be able to get to all of the Q&A, so I apologize in advance for that. The webinar is also being recorded. So after the event, we will be sending email to everybody who registered with a recording of the event, as well as additional resources, educational products that you can all check out yourself. So quickly, before we dive right in, just to give you an overview, we're today joined by staff from the National Science Foundation Ice Core Facility, which is located in Lakewood, Colorado, where I hear it's in the 40s, so not nearly as cold as it has been like the rest of the country. And the Ice Core Facility is a national facility for storing, curating, and studying ice cores that are recovered from glaciated regions of the world. It provides scientists with the capability to conduct exams and measurements on ice cores, and it preserves the ice cores for long-term, to create a long-term repository for current and future research. It is funded by the National Science Foundation Office of Polar Programs and operated by the U.S. Geological Survey, which is part of the U.S. Department of the Interior. And the University of New Hampshire provides scientific management for the Ice Core facility. So we love the collaboration that we have with all of our partners. One of the amazing things that we love here at NSF with the Ice Core facility is that it allows us an opportunity to talk about both the Arctic and Antarctic. So two poles that we focus on in the Office of Polar Programs, as well as some other glaciated regions of the world. So I want to quickly introduce our presenter today, which is who's Richard Nunn. He is our assistant curator at the Ice Core facility. He's been there for about 14 years and is very well known, I think, by the Ice Core community. And so we're so grateful that he's taking the time to speak with us today. In case you see some other people around, there's also Kurt and Theo who work at the Ice Core facility, who I believe are in the background. They're with Richard. So if you see some other faces, just want to let you know who they are as well. So without further ado, I'm going to turn over our presentation to Richard and take it away.
Awesome. Well, thank you so much. That was a great introduction. As she said, my name is Richard Nunn. I've been the assistant curator here at the National Science Foundation Ice Core Facility for going on 14 years now. So I spent a fair chunk of my life in that cold room right behind me doing cryotherapy for many, many years now. I know there's a bunch of people on here that I know. So friends, hello. For everybody else, welcome, and thank you guys for joining me. I've got a little presentation here that I'm going to just kind of run through to give you guys some background on what we do here at our facility, some of the logistics of how we actually go to places like Antarctica and Greenland, drill these ice cores and safely bring them back to the facility. And then we'll jump into some of the actual science of ice core research, what it is that we can learn from studying these things and why they're so important to us. And then I will also show you guys a brief video that will walk you through the freezer. I'm not going to take you in there in person because we lose all of our Wi-Fi signal as soon as I get in that box. But then you guys can actually see what it's like in my office, if you will. All right. So this facility was built in 1992 and turned on officially in 1993. It was designed with the idea in mind that they basically wanted to have a central repository for all of the ice cores that have been drilled by the U.S. Polar Program since the mid-1950s. And this is now, I believe, the largest singular collection of ice cores in the world. We have close to 25,000 meters of ice stored in our freezer, most of which are in these wonderful silver tubes you see here in this picture. For those of us here in America, that's about 15 miles worth of ice cores that we have. The vast majority of our collection, probably about 65% of what we have, comes from the southern continent. So this map of Antarctica shows the different locations that we have ice cores in our collection from. Each of those blue dots essentially represents a field location that we sent folks out to and drilled an ice core. A lot of these cores are drilled over the course of, say, one field season. They can be relatively shallow, just a few hundred meters. But the bulk of our collection comes from just a handful of cores that were, in some cases, drilled through nearly the entirety of the ice sheet. A good example you can see there in East Antarctica, the blue dot labeled Vostok. That is the deepest and oldest continuous core that we have in our collection. It was drilled back in the mid-90s, actually as a joint effort between the United States, France, and Russia. And we drilled to a depth of 3,600 meters. So that's a little over 2 miles into the ice sheet that we recovered this ice from. And the ice at the bottom of that core was dated to roughly 420,000 years ago. Now, there is another core that's older than that is stored at the University of Copenhagen. It's a place called Epicodome C, not too far away from where Vostok was drilled. That core dates back to 850,000 years. And to date, that's the oldest continuous ice core that's ever been recovered. There are plans to hopefully find the oldest ice. In fact, there's a big NSF push, a whole group called Coldex, the Center for the Oldest Ice Exploration. And we're hoping to get a continuous core that may be upwards of 1 to 1.5 million years old, which would be very exciting. What you guys are going to see a fair amount of in this presentation comes from one of our other cores in West Antarctica there. You can see the dot labeled WD. That's the Western Antarctic Ice Sheet Divide Core, which I know is a bit of a mouthful, so we just call that WAIS Divide. That's the most recent super deep ice core that the U.S. drilled back between 2006 and 2012. We drilled through 3,400 meters in the Western Antarctic and recovered ice that was about 70,000 years old from that core. And I have a lot of pictures from that, so you guys can see the logistics of how that core was drilled. We also have cores from Greenland in our collection. Unlike Antarctica, which is an international continent, Greenland is its own sovereign nation. It's still heavily associated with Denmark. And so a lot of the work done there is done by the Danes, usually with permission from the Greenland government, and at least in conjunction, if not with permission from the Danes as well. So a lot of the cores drilled in Greenland are actually stored in Copenhagen, but we have a handful in our collection. And in particular, the one you see there in the center labeled GISP-2, that is the Greenland Ice Sheet Project that was drilled between 1988 and 1992-ish. They went through the entire thickness of the ice sheet, which is at its thickest there in the center. It was about 3,000 meters of ice that they drilled, dating back about 100,000 years ago. And very uniquely, they actually hit bedrock there, and they drilled about 2 or 3 meters of bedrock from underneath the ice sheet. And then I don't have it marked on this map, but I finally got an opportunity back in 2018 and 2019 to go to the field myself as part of a Danish-led project with about a dozen other countries involved in the northeastern portion of Greenland there at a site called East Grip, which was the East Greenland Ice Sheet Project. So essentially we, as ice core scientists, will drill ice cores anywhere in the world where it's cold enough year round that whatever snow falls during the wintertime doesn't completely melt in the summer. So clearly the two major ice sheets of Antarctica and Greenland are going to be the best places to go do that. But we can also go to these high alpine regions around the world and drill into these mountain glaciers. They're typically not going to be as thick, and they're not going to date back in time as far as the major ice sheets, but it's important to get these ice cores from some of the mid latitudes, just so we get a more global picture for the story that these cores are telling us. In terms of how the ice forms, when we're drilling these cores, we don't actually start at ice right away. When we're drilling at the surface, we are going through a material that we call firn, which is spelled F-I-R-N. It's essentially compacted snow. If you ever get a chance to come and visit us, I can show you some of it, but it essentially looks like styrofoam. It's just really cold. It's compacted snow that is solid. It holds its shape, but for lack of a better term, it's fluffy. It still has air flowing through it. And it's not until we get to a zone, usually about 100 meters beneath the surface, what we call the lock-in zone, where the pressure is so great that that firn finally condenses down into solid ice. And at that point, any of the air that's been flowing through it becomes trapped, which is probably one of the most important aspects about ice core research, is that this is the only source on the planet we can go to get a direct measurement of what our atmosphere was comprised of tens of thousands or even hundreds of thousands of years ago. So when it comes to how we drill these cores, obviously the logistics of going to Antarctica are pretty involved. Our field window is usually pretty limited. Typically the field season in Antarctica ranges from about the end of October until actually right about now. Typically end of January, early February is when we start pulling people out of the field. The US bases a lot of our field work out of this place here. This picture is of a place on the coast of Antarctica called McMurdo Station. It is, or was, a military base many, many years ago, but as part of the Antarctic Treaty, no country is allowed to have a significant military presence on Antarctica. So they converted this to a civilian base, and it essentially acts as the jumping off point for a lot of our field work. The closest country to McMurdo Station is New Zealand, so we generally will fly our folks out to New Zealand. Again, this is typically in October sometime. It's not uncommon for them to get stuck there for maybe a week or two while they're waiting for weather to clear, so they can then fly out to McMurdo. I don't know about you guys, but I feel terrible for those poor scientists stuck in New Zealand in the middle of the summer. But anyways, once they do get their permission to fly out, the weather's clear, they go to McMurdo Station, they gather people, supplies, do all their safety training, and then once again, sometimes have to sit around and wait for the weather to clear so they can fly out to the field. And they will then do that on one of these aircraft. These are called LC-130s. There's a handful of these that are run by the US 109th Air National Guard. And they essentially took these old military cargo aircraft and they converted them specifically to work on the ice sheets of Antarctica and Greenland. And when I say converted, you can kind of see there, I basically mean they stuck skis on them. And so their job in the austral summer is to go down south and ferry people and supplies to and from their field camps. And then in the Northern Hemisphere summer, they head out to Greenland and they do the same thing out there. So this is an aerial view of the Waste Divide Field Camp. This is probably circa 2009, 2010, something like that. This is a pretty typical layout for a field camp in Antarctica, or at least one of the US camps. On the very bottom portion of this picture, it's kind of hard to see there, but they have what is called a skiway. It's basically the runway that they go out and groom from time to time to make it solid enough that these aircraft can actually land and take off. And then they have a large fuel depot, lines of supplies that don't necessarily have to be kept warm. And then in the middle of the picture there, you'll see these yellow structures. Those are called Jamesways. They're kind of hard-sided structures. A few of those are insulated. They have generators out there that do keep them warm. So there's some places to get out of the cold. I was told that in Waste Divide during the summertime, the average temperature was between about -20 and -40 degrees Celsius. So it was nice to have the mess hall and the rec room and other places like that to go get out of the cold. And then over in the top right corner, you'll see what they referred to lovingly as the tent city. And that's where folks sleep. I would say at night, but night's kind of a relative term in these polar regions during the summertime when the sun doesn't go down for about 3 months. And so that's where folks are sleeping when they're not working, is just in these nice little yellow tents. And then at the very top of the picture, you'll see what we call the drilling arch. That's where the actual drill rig was set up. That's where the core was being drilled. This particular operation did run about 24 hours a day. They would do usually 6 days a week, giving people at least Sundays off, as well as Thanksgiving and Christmas while they were down there. But otherwise they were running constantly. And that thing generated quite a lot of noise, which is why they kept it pretty well separated from camp, so that at any given time when people were sleeping in Tent City, they weren't being disturbed by the drill operations. So this is the inside of one of those Jamesways. It's a little home away from home. You can see that it's relatively cozy. They got a guitar there. There's a TV. I'm pretty sure they have to watch the thing at least once while they're down there. And this is where people are hanging out when they're not working or sleeping, essentially. This, on the other hand, is what folks are sleeping in. This is very similar to the tent that I spent my time in Greenland. We call these things Arctic ovens, and they are designed with this yellow material with the idea in mind that they're trying to essentially bake the inside of the tent. So since the sun doesn't go down while we're there, as long as it's not a cloudy day and the sun is sort of beaming down on these tents, you can actually get temperatures inside the tent that might be a couple degrees above freezing, which when you're living at -20, anything above freezing is pretty balmy. And then this is the bus to work. This is how we get our people and supplies around camp. These folks are heading out to the drilling arts that you see there in the background to start their day of work. Now, one of the issues with working in Antarctica is that we're only, as I said, there for maybe 3 months, and then we abandon the camp during the summertime or during the winter time. And as you can imagine, any structure slowly but surely gets buried in snow. So this is a series of pictures of the drilling arch from when it was first constructed in 2005 until the 2010 season. And keep in mind, they didn't actually finish drilling this project until 2012. So you can imagine the amount of work that went into digging everything out of the snow before they could even start the drilling process. And then by the last few seasons, they got to the point where they were just digging out enough that they could access the drilling arch. And you can see there by the end, they were parking on top of the darn thing. So this is inside where the drilling actually happens. You can see the drill there in the center, all of the equipment that they need, all of the spare parts. Something breaks down, you can't just run down to Home Depot to replace it. So they have to have a lot of equipment there to make sure things run smoothly. And essentially the way that this drill works is they have their drill bit, and attached to the back of that will be a barrel. And you can kind of see that here in this picture. For the Waste Divide project, the barrel was about 3 meters in length. So they would then run this entire drill mechanism down the borehole, and it's all attached to the surface via a very long winch. A very long cable, sorry, that's attached to a winch. And they would drill about 3 meters of ice, and then they would reverse the drill. And these things called core dogs, there you can see them actually tilting the drill down to go into the trench. And they would drill that 3 meters, they would break the ice off using these things called core dogs that you can see right there. And they would bring that whole 3 meter section of ice back up to the surface. So the actual drill time to drill 3 meters of ice was maybe 45 minutes to an hour. But then you also have to factor in the round trip time of going back down the borehole and coming back up. I was told that when they were nearing the end of this project, below 3,000 meters, it could be a roughly 5-hour round trip just to go down and drill 3 meters of ice and bring it back up. So that's part of why when we're drilling these deep ice cores, going 2 miles into the ice sheet, these projects take multiple field seasons to actually complete because it is a slow process and we have a very limited window of time to actually do this work. So once they bring these cores up to the surface, there's a whole nother section of that drilling arch where they have all of the equipment set up to measure the cores. They're basically measuring the depth, making marks on them, and then packing them so that they can come back to our facility where we will then actually process the ice. So once they've done all their depth measurements, they'll load these cores into these tubes, the same ones that we have in our facility that you guys saw in those earlier pictures. And then they put them in these boxes that we call insulated shipping containers. For the Waste Divide project, due to the diameter of that core and the size of these boxes, they could fit about 4 meters per box. And in a good field season, they'd recover maybe 600 meters or so of ice. So that generates a lot of boxes that we have to then bring safely back to us. So they will palletize these ice core boxes, and near the end of the season, they will load them onto one of those LC-130s. And they do what's called a cold deck flight, which is exactly what it sounds like. They turn the heat off in the aircraft, and they will fly from the field, in this case, Waste Divide, to McMurdo Station. That by turning the heat off, that easily keeps the ice cold. One thing that's important to note, though, is that we're not just concerned about keeping the ice frozen. Obviously, if it gets above zero and melts, everybody's sad. But what we have learned is that when these ice cores get to temperatures of around -15 degrees Celsius or warmer, those precious air bubbles that are trapped in there actually do start to migrate out, and we lose some of that valuable data. So our goal with these cores is to always keep them at least -20 degrees Celsius, giving ourselves a little bit of buffer. Obviously, flying in Antarctica, that's fine. Just turn the heat off. By the time they land in McMurdo, though, this will be, again, around now, late January. Things are cooling down, but it's still only about -15 degrees at the coast. So it's too warm for what we want to keep these cores stored at. So they designed these things that you see in this picture called safe core containers. They basically are these souped up shipping containers that are insulated. They have a redundant generator system attached to them. They can cool down to around -35 Celsius. And so they will unload the ice cores from the LC-130 and park them into one of these safe core containers and keep that thing cold. And that'll keep the ice safe while it's waiting for the container ship to arrive that will bring it back to us. So at the very end of the season, the last container ship to come into McMurdo is usually preceded by one of these icebreakers, because at this point, the sea ice is starting to grow again. So that will come in and clear space for the container ship that's going to bring all kinds of stuff from McMurdo back to the States, including our 2 or 3 safe core containers, depending on how much ice we drilled that season. So they'll load the containers onto that ship. They can plug it directly into the ship's power source. And then there's a technician whose entire job is to monitor these things and make sure that they're functioning for the roughly month-and-a-half journey that it takes for this ship to get from McMurdo to a place out in California called Port Hueneme. Once they get to Port Hueneme, they will then offload those containers, put them onto a flatbed truck, kick those generators on, and then they drive them out to here to Denver, Colorado, where we will then offload the ice and stuff it back into our freezer. So this was the shipment of ice that came to us in 2010. Fun fact, this was the largest shipment of ice that we ever received. It was actually 2 full field seasons worth of core that have been drilled. It was about 1,400 meters that came to us. And that geared us up for the longest and most complicated core processing line that we'd ever done, which was super fun for me because this was about 2 months after I started working here and I had no idea what I was getting myself into. So once the ice gets back to our facility, as you can see, we have all the empty shelves there. We'll unpack each of these boxes. We put the ice onto those shelves in order. And then that summer, a small army of grad students from all the different universities that were involved with this project would come out and spend the summertime with us doing what's called a core processing line. And in the case of this one, it was about a 3-month-long core processing line. And the idea with that is that we would take every single one of those meters of ice, we would double check all the measurements that they did in the field, and then we would run it around this sort of assembly line type setup of saws, cutting it into the various pieces that you see marked there on that top left picture. So essentially we're divvying the ice up into pieces that are going to be analyzed for water isotopes, for chemistry, and for the gases that are contained within them, as well as physical properties. And then making sure that we leave a good, say, 1/2 to 2/3 of the core behind as archive so that future researchers can access these cores and do much more refined and really like dive down deep into the science that they're wanting to do. So when it comes to how we actually process or what we're actually analyzing these cores for, there's a lot of fascinating stuff that we can learn from studying ice cores, but really the big driving force behind them is to understand our climate. Simply put, the ice cores are the best record of our Earth's past climate over the last 850,000 years. There's dozens and dozens of little nuanced details we have to study in these cores to kind of recreate what our climate is doing. But without getting into the nitty-gritty of that, these are the 3 main things we're trying to analyze these cores for. Namely, the atmospheric composition of those gas bubbles, how things have changed over time, specifically looking at greenhouse gases like carbon dioxide and methane, but we study pretty much everything that's in the atmosphere. We also can use these cores to recreate global temperatures and how those temperatures have changed over these long periods of time. And then, of course, time. It's pretty important that we can date these cores. If we weren't able to get a date on these, most of this other information wouldn't really mean a whole lot to us. So in terms of how we study the atmospheric composition, there's a number of different methods. Most universities are going to be focused specifically on one particular gas so they can fine-tune their instrumentation to look at, say, carbon dioxide or methane. So this is a good example of the Scripps Institute in La Jolla, California, where they're doing methane analysis. So essentially, they'll take their little sample of ice, which for this one, they need something like 400 grams of ice that's not broken and doesn't have any fractures in it. And they will put it into a small vacuum sealed chamber that you can kind of see there in the center of the picture. And for methane, they simply let the ice melt. And that releases those gases that they can then pump out and run through a machine called a mass spectrometer, which can calculate the concentration of the methane, which in our atmosphere is measured in the parts per billion. Folks that are doing CO2 have a similar setup with one large caveat. Carbon dioxide dissolves in liquid water, so they can't just melt their sample. So they will also put it into a vacuum sealed chamber, but it's inside of a freezer. And then they will use a variety of techniques, my favorite of which was described to me as a high-tech cheese grater, to essentially grind or crush or break the ice up, allowing what they call dry extraction. They can pull that CO2 out without melting the ice. And then a similar process, they run the CO2 through these mass spectrometers and they can calculate its concentration, which in our atmosphere is measured in the parts per million. The temperature data is derived by studying what we call the stable isotopes of hydrogen and oxygen. So basically, we're looking at the water molecules that actually make up the ice itself. And the idea behind this is that we have, in the world's oceans, we have our H2O, and we have our normal water, and then what we call heavy water. And according to this chart here, as you see, about 20 out of every 10,000 atoms of this water is going to have an isotope of hydrogen or oxygen that's slightly heavier. So in this case, we're looking at the ratio of O16 to O18. And the reason this is able to tell us about our temperature is because there's a process that happens when water evaporates, transports, and eventually precipitates called isotopic fractionation. And basically what this is saying is that as these systems of water move towards the south and get colder and they condense, they eventually start to precipitate out the water. And they generally will precipitate out those heavier isotopes first. So by the time this system of evaporated water reaches Antarctica or Greenland, it will be depleted of some of those heavier isotopes. And the amount of that depletion is heavily dependent on the temperature. So we can look at, say, temperature records of this transportation from the mid-latitudes to Antarctica. And if we're looking at two different temperature profiles here, the dark blue being a little bit warmer than the light blue, when we look at the ratio of those heavy isotopes that are left by the time it precipitates in Antarctica, it is a direct correlation to the temperature itself. So by looking at these isotopic fractionation processes in modern times, we can then apply that to these ancient ice cores. Because those isotopes are stable, they don't decay over time. They essentially trap that temperature data and allow us to reconstruct what the temperature was 10,000 years ago or 100,000 years ago. And then, of course, to date the cores, there's a bunch of different methods we use for these, generally done somewhat independently, and then they will come together and hopefully they agree. But most of these dating techniques generally have to do with the fact that there is a bit of a seasonal variation in the composition of ice from summer to winter. In some places like Greenland, we can actually visibly see this. As you see on the bottom there, those beautiful layers are from one of the colder periods of our Earth's history, when there was a lot more dust in the atmosphere. And basically in the colder, drier periods of the year, you have a higher level of dust in the atmosphere, and therefore more dust falls onto the ice sheet, giving us these nice cloudy bands. And then in the summertime, when there's less dust in the atmosphere, we get these nice clear bands that don't have quite as much of that dust concentration. The same process happens in Antarctica, but the dust load is significantly different because there's not near as much dust being blown over the Antarctic continent. So when we look at an Antarctic ice core, it's clear as glass. We can't visibly see these layers, but we have instrumentation that could pick them out. There is a machine that we use called the electrical conductivity machine that runs electrical probes over the ice, and it tests how well electricity flows through the ice itself. If you had pure ice, just like if you had pure water with nothing else in it, it actually doesn't conduct electricity. It's all of the materials within water or within the ice that allows electricity to flow. So if you have a higher concentration of dust particles, electricity is going to flow through that part of the ice better. And that's where we get charts like the one you see on the top left there. If you ignore that real big spike for a second, what we're basically looking at here is about 50 centimeters of ice and how the electricity is flowing through it. So each of those peaks and valleys is showing a change from summer to winter as that conductivity goes up and down. And this allows us to get a continuous date of the ice core from the surface all the way down to the bottom. They can then verify that information when we do our chemical analyses. Amongst all the different chemicals that people are studying in these ice cores, there are some of them that are very specifically related to seawater. And if you imagine during the winter time when sea ice grows around Antarctica and Greenland, it blocks a lot of the ocean chemistry from falling onto the ice sheet. And then in the summertime, as that sea ice melts, a lot more of that ocean chemistry is falling onto the ice with the snowfall. So we get these chemical signatures that, very much like those electrical signatures, will rise and fall from summer to winter, giving us a seasonal ability to count these layers of the cores. Then when we do see a big spike like what you see on that chart, that's what happens when we run across something like what you see on the top right of the picture. That is a volcanic ash layer. The one in this picture is very unique because it's incredibly thick. We find volcanic layers in cores all the time. The Waste of Ice Core, there was probably over a couple hundred volcanic events that were recorded in that, but generally they're from volcanoes so far away that it's just a tiny little pencil line of volcanic ash that you can see. But the conductivity will get a big spike when it runs across an ash layer, so we know that there's something there. What's unique about these ash layers is that while there's usually not enough material to do what we call radiometric dating directly on the ash itself, we can look at the chemistry of it and identify its source. Every major volcano in the world has its own unique chemical fingerprint whenever it erupts. And so we can identify exactly which volcano these ash layers came from. And then going to that source, we can date that volcanic layer where the volcano actually erupted. And that gives us a very, very specific age when we find these volcanic layers that we can use to make sure our continuous dating technique is working. Now, in terms of that volcanic layer, that is, to the best of my knowledge, the thickest volcanic ash layer that's ever been found in an ice core. That came up in the Waste of Ice Core. It shocked everybody. Nobody expected to see it there because we've not seen that in any of the other cores from Antarctica. So that tells us that it had to have been a local event because it was so thick and it was so localized in just that one area. But chemically, it does not match any of the known volcanoes in Antarctica, such as the famous Mount Erebus. So the going theory is that most likely this is from a volcano that was beneath the ice, what we call a subglacial volcano. Which with a lot of the subglacial sort of imaging we've been able to do of Antarctica to get a picture of what the landmass looks like underneath that 2 miles of ice, we do see several features that look distinctly like volcanoes. So the idea is that this volcano erupted. That one was dated to about 21,500 years ago, with enough force to melt through 1.5 miles or so of ice and deposit this very thick but very localized layer of ash. So once we have all this information, we've got the gas information, we've been able to recreate temperatures, and we've been able to date the cores, we can then do what scientists love to do, and that's make a bunch of squiggly lines and then try and interpret what those mean. So this chart, excuse me, is showing data from the Vostok Ice Core. We're seeing about 420,000 years worth of climate data on this chart. So starting on the top line here, that blue line is showing carbon dioxide levels from 420,000 years ago until modern times. And they fluctuate between about 200 parts per million in these cold periods and 300 parts per million in the warm periods. The green line is methane, very similar to CO2. It fluctuates from about 400 to 700 parts per billion during this time. And then the red line is our temperature, where 0 on the right there is about what temperature we are today. And then on the bottom part of that red line is about 8 degrees Celsius colder. So we see this cycle where global temperatures vary by about 8 degrees Celsius. So there's a few things that jump out at us when we look at charts like this from ice cores. The first and foremost is that the greenhouse gases and the temperature more or less move in lockstep with each other, which didn't really come as much of a surprise because we've understood the physics of the greenhouse effect for quite some time and how inextricably linked greenhouse gases and temperature are. But what was really exciting with these ice cores is that we can now see numbers. We can see how much these things changed and how over what period of time they changed. And that rate of change is really important to understanding what's going on today. The other thing that we see is that there's a bit of a regular cycle going on. We get these periods of about 100,000 years or so where temperatures are about 8 degrees colder than they are right now. And then over a couple thousand years, they'll warm up, stabilize for 10,000 years, and then cool back off. Once again, this is something that scientists have kind of known about for some time. These are what we call the glacial and interglacial cycles. Our planet entered into our ice age about 2 million years ago, and we are smack in the middle of it right now. We just happen to be in one of these warm interglacial periods. There's a lot of different reasons why the planet went into an ice age, and we're not going to go into too much of that, but suffice to say, when the planet is cold enough to actually have these ice caps, that regular fluctuation of about 8 degrees Celsius, while it doesn't seem like a whole lot, has a pretty big impact on the planet. If we were to go back to the last glacial maximum, a little over 10,000 years ago, this is what North America would have looked like. That is what we call the Laurentide ice sheet. And to give you a little bit of reference, at that point in time, New York City would have been under probably close to 1 mile of ice. As you can imagine, an ice sheet that large growing leaves its mark behind. Speaking of New York City, if you ever go to Central Park and look at any of the rocks exposed there, you'll see how these striations moving in the same direction. And that's evidence of the glaciers scouring the land 100,000 years ago as the planet was cooling down and these glaciers were growing. On the other end of that, when things start to warm up and we come out of those glacial cycles, those glaciers retreat. And as they do, all of that material, all that debris that they picked up gets dropped in these massive debris piles that we call glacial moraines. One of my favorite glacial moraines to go visit is Cape Cod, Massachusetts. Pretty much the entirety of that cape, as well as you can see a lot of Long Island, is just filled with all of these glacial moraines from when those glaciers retreated about 10,000 years ago. So again, in the geologic record, we've seen evidence of this natural warming and cooling, and we had a kind of general idea as to what time period it took over. But with the ice cores, we can really get down into the nitty gritty of that and see exactly how much things were changing and exactly how fast they were changing. And that's part of why there's a bit of concern these days. When you look at this chart here, this is showing the Epoca Dome C core, which is about 850,000 years of climate data. We never see carbon dioxide levels rise above about 300 parts per million. And the time it takes for them to go from 200 to 300 parts per million, equal to about 8 degrees Celsius of temperature change, is usually a couple thousand years. If we zoom into just the last 2,000 years, this is data from the Law Dome Ice Core, we see that the CO2 levels were pretty consistent, about 280 parts per million in the pre-industrial era. And then right around the time of the Industrial Revolution, those levels started to rise. And they began rising exponentially as we started burning fossil fuels exponentially. So we know that this excess greenhouse gases in our atmosphere, the excess of methane and the excess of CO2, is due to human activity. We can tell that from the isotopic signatures as well as a number of other factors. The big question is, what is that going to mean for our climate? And if you look at that bottom chart that's showing the temperature data covering the same 2,000-year period, you see that it's relatively stable. In fact, there's even a bit of a cooling trend going on, which is the case that we see in most of our ice cores, is that very gradually the Earth was starting one of these cooling trends. And then in the last century or so, that has reversed to a rapid warming trend. And my final slide here to give you sort of an idea as to what we are looking at in just the last 150 years. That's the average global temperatures in the 20th century. And that gray line is the carbon dioxide levels. So we know that humans are responsible for the excess carbon in the atmosphere. The big question now is, what is that going to mean for our climate moving forward? And the best way to answer that is to really understand how the climate cycles work in the natural environment and then figure out what's going to happen now that we've changed things. And because the ice cores are the best record of what the climate has been doing naturally for the last few 100,000 years, they're the best piece of information we can look to try and figure out what we can expect to see moving forward in terms of how much things are going to warm and over what period of time they're going to warm up. And that really is the big concern. When we look at the natural cycles of our planet's warming and cooling, we see that it warms and cools all the time. That's not necessarily a big deal. A warming planet, if it took place over a couple thousand years, would be fine. But when we condense 2,000 years worth of warming into a century or two, that puts a lot of strain on the ecosystems around the world that we rely on for our food and for our water and everything like that. So all of these scientists that are now trying to look to the future and make these computer models in terms of what we can expect the planet to do based on what we do in terms of our emissions, they use a lot of this ice core data to inform those models, and that will hopefully help us to predict what we can expect to see in the next 50 to 100 years. And that to me is why I think the ice cores are probably one of the most important resources we have, because they give us all of this wonderful information. So with that now, I'm going to take you guys on a very brief little tour of the actual freezer itself. Just give me one moment to switch over here. And then I will be happy to take questions at that point. So this is our freezer. It's a giant steel box inside of an even larger concrete warehouse. This first room that we're walking into here is what we call the exam room. This is where we do most of our work on the ice cores. It's kept at a balmy minus 24 degrees Celsius. That's about minus 10 degrees Fahrenheit. It's warm enough that we can actually work in there for decent periods of time, half hour, 45 minutes or so. And then I've got a couple of pieces of ice here that you guys can see. I'm going to pause on this so you can see the wonderful layering in this core. This is a core from the Greenland Ice Sheet project. That particular piece is from 1,840 meters beneath the surface. That's about a 16,000-year-old piece of ice, and you can see the layering real nicely in there. There's about 40 years worth of snowfall recorded in that single meter. And then we'll move over here to a piece of ice from Antarctica, and you'll see that volcanic ash layer that I was telling you guys about. That's the roughly 21,500-year-old volcanic layer. And as you guys saw in the earlier picture, it used to be in the cylinder. This is one of our archive pieces that was cut out of it. So then we're going to swing around here. You'll see that I have a computer. It's in a nice insulated box, so I can actually update my database as we go. Our wonderful mascot's there in the background. We've had Mr. Freeze for probably 30 years, and we just got him a companion in the form of Elsa about a year or two ago. And then we're going to go back into the main storage. And you'll see here the temperature for this room is pretty close to minus 40 degrees, which happens to be the number where Celsius and Fahrenheit cross over. So this is how we store our 25,000 meters of ice in these wonderful silver tubes. This sort of gives you an idea for how absolutely massive this collection is. Yes, the video is a little choppy, but you guys should be able to see that just fine. I'm walking to probably the worst part of the freezer to work in. Those fans right there are blowing cold air right in your face. And I don't know what the wind chill is at minus 40 with a 10-mile-an-hour wind, but it's cold. So we are walking through thousands and thousands of years of history here, all kept frozen. It still fascinates me to think that we are storing snow that fell thousands of years ago and has not melted yet. I'm sure all of you in the States here, at least in the places like we were at, we experienced temperatures like this over the weekend. But fortunately, it warms up and the snow melts. That does not happen in Antarctica or Greenland. So that's the entirety of the collection. As you can see, we are quite full. We're actually in the process of getting a new freezer built to transfer. So we'll have a newer state-of-the-art freezer, hopefully in a couple of years, to keep on going for the next 30 years. And then this room is our, what we call the dock. It's nice and balmy in here. It's just above freezing. It's like maybe 35, 36 degrees Fahrenheit. After hanging out at that minus 40 temperature, this room feels pretty toasty. And then we're heading back out into the warehouse. And that concludes the tour of the Ice Core facility.
Awesome.
Right.
Well, thank you so much, Richard. That was so fascinating. I've learned a ton about chemistry and just this process, and the thought of the logistics of getting ice cores from these remote areas to your facility in Colorado also kind of makes my head spin. So I really appreciate you running through that. I just want to remind everybody that if you have questions, please feel free to drop them into the Q&A box. We're going to try and get through as many as we can, knowing we probably won't be able to get to all of them. But I would like to just start off with simply, you've been talking about ice for so long. A lot of us experienced bitterly cold weather, maybe ice on the roads over the weekend and this week. Can you just start by explaining how is the ice that you have, the glacial ice, this historic ice, different from the ice that I have like in my cup, right? And how do you tell what that difference is? I know you mentioned fern layer and compaction, but just
Yeah. So we call the ice that we're drilling into, it's called meteoric ice, which basically means it's ice that formed from meteorology. So water, or in this case, snow that fell from the atmosphere and then didn't melt. And so over time, as that compacts, it does eventually crystallize. If you were to look at just say a regular ice core and an ice cube from your freezer, you'd probably notice a big difference in that the ice core is clear. And if you look real closely, you'll see bubbles in it. Whereas the ice from your freezer, it's going to have that sort of milky white center. And that's because that was just water that was then frozen. And so those ice crystals grew inward and eventually sort of melded with each other. And that's why you get that weird opaque kind of center of an ice cube. Whereas our cores are snow that just compacted and compacted and compacted over time. We actually have special microscopes that we use to study the physical properties of these ice, where we will make thin sections that are shaved down to just a few microns thick, and we look at them under polarized lenses, and you can actually see individual little ice crystals. We also did a thin section of an ice cube, and you see these just shards of crystals that kind of grew into each other. So when you look at any kind of ice as a thin section under a petrographic microscope, you can tell whether it was clear ice that was grown, like for ice sculptures, an ice cube that was just frozen in your freezer, a hailstone, or meteoric ice. They all look different under a microscope if you can see those mineral or the crystals.
Okay. All right. Well, that's a good basis again as we dive in.
Cool.
So we've had a few questions, so I'm kind of going to try and put them into one, about the same topic. Yeah, I'm kind of trying to combine them. So we've been talking about ice, and there are a few people who are wondering about how these ice cores, like, do you ever get bedrock as part of the ice cores, and then relatedly permafrost? So kind of that permanently frozen ground that Alaska and other parts of cold climates have. And then similarly, right, in relation, how do these ice cores differ from what people may be more common, earth cores, right, from the ocean floor and similar locations?
Yeah, so those are all done by different people. You've got rock cores, which generally are drilled mostly for mineral and oil and gas exploration. Sediment cores are actually part of the climate story as well, and a bunch of other things that are drilled in ocean and lake environments. And then permafrost is its own monster as well. We don't deal with any of those because we don't want that kind of contamination to get into our pristine ice cores. So there are permafrost labs. They usually have their freezers significantly warmer than ours, but still below freezing. In fact, the warehouse that we're in, it has a giant rock core storage space. They don't have to worry about temperature because they're rock cores. So yeah, those are all very different things. The technology to drill these cores can be quite similar. There's a fair amount of crossover there, obviously some differences, especially working in the extreme cold that we do. When it comes to bedrock, though, that's a very precious resource to get bedrock from underneath the ice sheets, and it's not very common. There's been a handful of cores from Greenland where they have drilled bedrock. We generally don't do that in Antarctica for a couple of reasons, but primarily because we have discovered the Antarctic ice sheet is significantly thicker than Greenland. It's about 4 kilometers on average. And the pressure of that much ice sitting on top of actual bedrock allows, surprisingly enough, for liquid water to exist at the base. In fact, there are entire lakes and streams underneath the Antarctic ice sheet, some of which are connected. And there was a few of those that they drilled into using very specialized equipment that was pristine. It was purified. They used UV light. They made sure that there was no contamination. They recovered some water from one of these subglacial lakes and discovered several thousand species of unknown bacteria. So we know that there's an entire ecosystem underneath the Antarctic ice sheet. The problem is when we're drilling these ice cores, to keep those boreholes open because the ice wants to squeeze shut, we have to put drill fluid. And the drill fluid is not terribly environmentally friendly. And so we don't want to contaminate these lakes and streams. So when we're drilling in Antarctica, we usually stop well above the bedrock in order to prevent that from happening. But I know if there's 4, maybe 5 cores in Greenland that have reached bedrock. One of them we have here. I've got about this much of an actual piece of rock from underneath the Greenland ice sheet.
That's pretty cool. The Greenland ice sheet is a fascinating part of the globe. So you get these ice cores and you store them. Now, your oldest ice core, remind me, is from 1956?
1956 was the Camp Century core drilled in northwestern Greenland. Yep.
Okay, fantastic. So you have this ice core from 1956. Are there concerns, or if there are, what are they, about these ice cores that are, I mean, you're looking at, what is that, 70 years old, in terms of the degradation potentially of the ice core, or even of those air bubbles that you were talking about, and how critical that is for understanding climate data from the past?
Yeah, that is a really good question. There is a bit of degradation. It takes a long time, and in general, the colder we can keep the ice, the longer the atmospheric air stays in those cores. But when we start looking at things that were drilled prior to the 1970s, nobody's going to really use those for any more gas analysis. The chemistry doesn't change, the isotopes don't change, but the gas information does eventually change. And so generally, I would say, I don't, there's probably been some studies done on this, but anything more than like 30 years in storage, and you're probably not going to get anybody interested in doing gas analysis.
Okay.
The other aspect of degradation is us just making sure that we don't allow this to happen. The air in our freezer is incredibly dry. The humidity is nearly zero. Dry air like that, even though it's super cold, when it blows across the ice, it plucks molecules of water off of there, trying to saturate the air. And so it's a process we call sublimation. If you ever leave your ice cubes in your freezer for too long, you'll notice they just kind of go away. The same process is happening there. So to prevent our cores from sublimating away, we store them inside of sealed plastic bags that are then inside of those tubes. And I did an experiment once. I just left a fake ice core that I had made that was maybe this big in diameter out, and it took about a year for it to just completely disappear.
Okay. All right. So they might not last forever if they're not taken well care of.
Yeah, and that's what my job is.
So we've gotten a few questions about kind of data and how that works, and this collaboration with universities. But before I get to that, a quick question: have you found anything? People are asking about animals, fossils, anything like that in the ice cores, and if you do, what happens?
Yeah, so 99% of the cores are clear. They all look the same. So we get really excited when we see something like that volcanic ash layer. The thick volcanic ash layer is probably the coolest physical thing I've ever seen in a core before. But I always do like to tell this story. There's a glacial core that was drilled, and I for the life of me can't remember which glacier it was in, but a mountain glacier, and they found a grasshopper leg, just the leg. I don't know what happened to the rest of the grasshopper. And I've seen like little bits of, beetle shells or a little piece of grass or something like that in some of the glacial cores. That's a little more common in mountain glaciers because you do have actual biological life not too far away that could get blown in on a storm. When you go drill in the middle of Antarctica, there's nothing that lives out there. So the chances of finding anything biological are pretty slim. Not zero, because occasionally birds do get blown over the ice sheet and unfortunately die, but very, very small chance of drilling a core this big that we're going to hit anything that happened to die 10,000 years ago.
Right. Okay. All right. So we're not finding any like frozen dinosaurs.
We haven't found the aliens or the thing or the Stargate yet, but
okay. You never know. So when it comes to, I'm going to go back to that data question I mentioned. So you get these ice cores. And let's say you're part of the Coldex team, which is going on now. So we've got University of Minnesota, you've got, I want to say UC Boulder is part of that. Is that right?
Northwest, Princeton.
Northwest, Princeton. Okay, so you've got all these universities. So who kind of gets first dibs, if you will, on the ice, on the data? And then once that processing has happened, how do other scientists get to access either the data from those ice cores for their research or other pieces of the ice core?
Yeah, no, those are great questions. So for big projects, especially something like Coldex, but even, Waste Divide or the South Pole Ice Core, there's collaboration between a bunch of universities. The folks all get together because, one university is going to be doing the isotope analysis. Another one's going to be doing the methane. Another one's going to do the CO2. Then this one's doing the dating. And so before they even start drilling, there's generally a consensus of these are the groups that are going to be doing the initial run through of the analysis of this core. They've decided how they want to divide it up with one of those little cut plans before they've even drilled it. And so those are the groups that get first dibs on the core. Once all of that data is published and essentially I forget the terminology for it, but when the grant for that project has basically expired, then that core becomes available to essentially the general public, in a sense, to anybody else who wants to do research on it. There is a method to go and ask for access to these samples. It's on our website. We have a form that you fill out. Basically, it's called a sample request form, and it has what samples you want, what science you're doing on them, how much of the archive it's going to take, and why this is important. And oftentimes they're either trying new techniques out to get better data, or they're just doing more refined look, higher resolution of a particular climactic event within this ice core. That goes through UNH, who does our science management, and then they will send that out to what's called the Ice Core Working Group, which is a rotating group of scientists within the ice core community that will review these proposals and say, yeah, this is great science. I think it's worth, giving them this archive, or we need some more clarification, some more questions, or oftentimes it's like, this is a new methodology. Let's give you a core that we deem less scientifically valuable to prove your methodology is actually worthwhile. Then we'll give you access to the fancier stuff. So there's the entire process of that. And then because this is all funded by the National Science Foundation, which is our taxpayer dollars at work, when all of this information is published, that data then becomes publicly available. And most of that is stored on the National Oceanic and Atmospheric Administration's website.
Okay, so National Oceanic Atmospheric Administration, that's NOAA. More common people might know NOAA. So you can check it out if you want to see the data. And I believe the Ice Core Facility website has a huge searchable database of the ice cores that they have in their facility. So in addition to going and visiting it, if you are in Denver, which I plan to do next time I find myself there.
And I will mention as well, we like to advertise this in that our freezer is relatively full. We're getting a new one that's going to be a little bit bigger, but we have about close to 2,000 meters of ice that we have is on what we call our deaccession list. These are cores that are deemed less scientifically valuable because maybe their metadata is not as great, or they just haven't been studied a long time. They're usually relatively shallow, not terribly old. Sometimes they're not in great condition, but we keep them for outreach. And so people can request ice for outreach for artistic purposes or for classroom studies, things like that. And it helps us as well because it clears a little bit more space for the newer ice that we're going to be having incoming. So there's a whole thing on our website about deaccession ice that teachers feel free to look at. It's a great resource.
I love that. And we'll include all of these links in our follow-up email. So, all right, 3 more questions before we run out of time here. So one is, can you use ice cores from different parts of the globe? Can you see them line up with maybe different global events?
Absolutely. So in Antarctica, it's very easy to use those volcanic layers I was talking about to tie them together, but there's a lot of work where we're looking at a core from Greenland and a core from Antarctica, and we see the same climactic events, and so we can tie them together that way. And it's really nice when that matches up and the dates also agree. That lets us know that all of our techniques are actually working. But it's super important because as the climate changes, things happen differently in the northern hemisphere than the southern hemisphere for a lot of reasons. There's a whole lot more landmass up there. The air currents are different and everything like that. So there are some interesting studies that are done on comparing, say, the Greenland Ice Sheet Project core to the Waste Divide core and what they call this sort of polar seesaw effect, where you might see warming on one pole and cooling on another pole. But yes, the larger scale events are very well studied, and makes it very easy to tie pretty much any ice core to any other ice core.
Well, I love seeing that connecting. And then do you have, I'm hoping, alarms if there's an issue in your freezers? People want to know what happens.
This thing right here is our duty phone, and it yells at me if anything goes wrong.
Okay.
We have backups within backups within backups. We have a backup generator. Pretty much anything that would take more than a couple of hours to repair, there's a backup version of. And there's an entire computer system that monitors everything. And if anything goes out of whack, if a compressor fails, if a temperature gets too warm or anything, it will send out an alarm to that phone, to the Federal Protective Services, to our mechanical contractor, basically call in the cavalry. And as I mentioned, we've been running for 35 years and have never been shut down due to something failing for more than a couple of hours.
Okay.
And when we were doing a big retrofit of the evaporative coolers, we were purposely shutting the freezer down for about 8 hours a day while they're doing work. And after being off for 8 hours, the back freezer warmed by about 2 degrees. So we've got, between the insulation and the thermal mass in there, we have a fair amount of time if something does go wrong. But we got to get.
All right, good. Whew, I got nervous for a second. So finally, you know, we're coming up to the end, and I'm sorry we haven't gotten to all of the questions. The Ice Core facility, I'm going to send them all of the questions that were submitted. They have social media, so you might be able to take a look at what they've been posting, get some of your questions answered that way. And so I will be including resources for everybody in the email, like I mentioned. What would you say to someone who is interested in becoming an Ice Core researcher, you know, hoping that we've inspired some folks? Maybe there's some grad students, younger students who are like, this sounds like a cool job. I want to go live in a yellow tent for 3 months and be cold, but then get to see these awesome ice cores and study our climate. What would you say to someone who wants to get involved that way?
I would say definitely do it. This has been one of the most amazing communities I've ever been part of. The Ice Core community is relatively tight knit. Just absolutely wonderful and brilliant people that I get the opportunity to work with. And we all are very passionate about what we're doing. We understand the importance of it. And for anybody who's interested in pursuing that kind of career, most folks get their start in some kind of environmental sciences, a lot of geology background, a lot of chemistry background as well, meteorology, things like that. As they start diving deeper into, say, grad school, that's when they start focusing more on glaciology or paleoclimatology. That's when they really get their hands on ice cores. And then, of course, when people get into their PhD pursuits, they're very narrowly focused, like, I'm just writing a paper on the methane record of the waste of ice core. But yeah, any sort of environmental science is a good way to dip your toe into it and then decide where you want to go from there.
Awesome. All right. Well, I want to thank everybody again for joining us today. I hope you learned something new that you can bring back to your friends and family. Here's our social media as well as some key websites. You can use that QR code to just bring it up on your phone for easy access. These will all be in the email that I send. Again, Richard, I just wanted to thank you so much for your time and your expertise in talking about ice cores. And with that, we will say goodbye. I'll keep this up for another minute as folks hop off if they want to jot down the information we have. And thank you again. Keep an eye out for more live events that we have about polar science. Thank you.
Thanks, everyone.